Glendale Community College. We are here to work on Chem 130's Chapter 13 on stoichiometry. We are going to learn about mole ratios first of all. So when we have a balanced reaction, we just learned how to balance them and put the coefficients in front to balance them. But what do those numbers really mean? For example, look at this reaction. We have two NO gases plus one oxygen O2 gas making two NO2 gas molecules. So we have a 2, a 1, and a 2. Those are ratios for our molecules, right? We can say there's 2 NO molecules plus 1 oxygen molecule making 2 NO2 molecules. But who can actually go into the lab and 1 molecule, 2 molecules, roll them together and have our reaction occur? Okay, we can't do that. Molecules are too small. Instead, we use handfuls of molecules. Do you remember what a handful of a molecule is? Yes, it's a mole. A handful is approximately 6.02 times 10 to the 23rd molecules in a handful. So we can also think of the 2-1-2 ratio as mole ratio. So if we look at that reaction, we can also think there's 2 moles of NO plus 1 mole of O2, making 2 moles of NO2. So they can also be mole ratios besides molecule ratios. Okay, let's go to the next reaction with nitrogen in front. So how many molecules are there? You're correct if you said 1. Sorry about that. Just 1 nitrogen molecule. What about hydrogen molecules? How many are there? Yeah, there's 3. 3 hydrogen molecules are needed for that reaction to go with the 1 nitrogen molecule. And what do we make? Yeah, 2 molecules of ammonia, NH3, 2 molecules of ammonia. Now remember, we can also say these are mole ratios. So how many moles of nitrogen are there? Just 1. And then how many moles of hydrogen? Yep, 3. And we're going to make how many moles of ammonia? Yes, 2. So those coefficients in front, the 1, 3, and 2, give us molecule or mole ratios. And mole ratios are much more handy because we can't go into lab and pick out molecules and react them together. We have to go and scoop up a handful of molecules, so mole ratios are much more handy. So let's try to apply this to a new reaction. We have iron Fe2O3, so that's iron 3 oxide, plus we're going to react it with carbon monoxide, and we're going to get some solid iron out of that and some carbon dioxide. Now what do the numbers in front mean again? Correct, those can be molecule or mole numbers. So how many iron 3 oxides are there? 1 mole's worth, correct. How about carbon monoxide? You're correct if you said 3 moles worth. And how much solid iron do we make? 2 moles worth, good job. And how about carbon dioxide? Yes, 3 moles worth. Now we can make ratios with these moles by putting a top number over a bottom number. For example, I can have 1 mole of Fe2O3 per 3 moles of CO and make a fraction out of it. Or I can say I have 3 moles of CO over 1 mole of Fe2O3. Or I can say I have 2 moles of iron over 3 moles of CO. The ratio depends on what the question's asking us. So we're going to use mole ratios in some problems. We have 2 problems on the screen right here, 1 and 2. Let's give them a try real quick. Number 1, how many moles of iron can be formed from 10.2 moles of carbon monoxide? So remember this chapter, stoichiometry. I'll give you a hint. Stoichiometry problems always involve 2 chemicals in a balanced reaction. Let's look at this question again. How many moles of iron, there's a chemical, can be formed from 10.2 moles of carbon monoxide? There's another chemical. We have 2 chemicals and we have a balanced reaction up there. It's a stoichiometry problem. It's going to involve a mole ratio. So let's start with what we're given. 10.2 moles of carbon monoxide. Which chemical is carbon monoxide? CO. Very good. So we're going to start with 10.2 moles carbon monoxide. Next, we're going to have a mole ratio. Now, whatever we started with has to go on the bottom because units cancel out top to bottom. So how many moles of carbon monoxide are there in the reaction? 3, right? So 3 moles of carbon monoxide is going to go on the bottom of our mole ratio for this question. And the chemical we're trying to find goes on top of the mole ratio. What chemical are we finding out about in this question? Solid iron, right? The iron. So the moles of iron goes on top. How many moles of iron are in that reaction? 2. 2 moles of iron is on top over 3 moles of carbon monoxide. And so we set it up like this. 10.2 moles of carbon monoxide times the fraction, the mole ratio, 2 moles of Fe over 3 moles of CO. Moles of CO cancel out top to bottom. And the answer, when you put that in your calculator, 10.2 times 2 divided by 3 equals 6.8. That's what the calculator says, 6.8. Why'd we have to add a 0 on the end? Oh yeah, sig figs. Sig figs never go away with math. So 10.2 has 3 sig figs. The mole ratio, by the way, is exact. It's exactly 2 to 3. Exact numbers don't count in your sig figs. So the answer has to have 3 sig figs, just like 10.2, so it's 6.80. Perfect. We have one more question to try. Number 2, how many moles of iron 3 oxide are needed to form 17 moles of carbon dioxide? I'm going to let you figure out, what are we starting with? What do we know? If you said 17 moles of carbon dioxide, you're correct. Which chemical is carbon dioxide? CO2. Very good. So we're going to start with 17 moles of CO2. Now it's time for our mole ratio. What mole ratio is on the bottom? What mole is on the bottom? Has to be what we started with, which is the CO2. How many CO2s are there in that reaction? 3. So 3 moles of CO2 is on the bottom. The chemical we're finding is on top. What are we finding out about? Iron 3 oxide. So Fe2O3 is on top. How many Fe2O3s are in that reaction? 1. So 1 Fe2O3 is on top, so the setup looks like this. We've got our 17 moles of carbon dioxide times the mole ratio of 1 mole Fe2O3 over 3 moles of CO2. Moles of CO2 cancel out top to bottom. And our answer is 5.7 moles of Fe2O3. Now that was rounded. Why did we round it to 5.7? Why not 5.682347, etc.? Why 5.7? Sig figs. 17, the number we started with, only had 2 sig figs. So 5.7, we can only have 2 sig figs. All right. Good job. Thank you.